Hello learner, I am Ajay Kumar, Assistant Professor, Central University of Himachal Pradesh, Department of Computer Science. Today we will study about the comparative efficiency of algorithm that contains linear algorithm, logarithmic complexity, quadratic complexity and exponential complexity. So, generally what we do regarding the algorithmic comparison. So, in next slide we will study about the what is the concept behind the efficiency analysis of algorithm. So, if we are given an input to an algorithm, we can exactly compute the number of steps our algorithm execute. So, how many steps are there during the execution of algorithm, we focus about the efficiency of an algorithm. So, we can also find the count of processor instructions, how many instructions are there. So, generally efficiency depends upon the number of steps, or we can say the number of count of processor instructions, or we are interested in identifying the behavior of our program with respect to input supplied to the program based on the type of input. Analysis can be classified as following, right? We can say best case analysis, worst case analysis and average case analysis. So, if we talk about the best case analysis, generally best case means we already studied about the asymptotic notation. In terms of asymptotic notation, we can say best case means omega notations generally. So, input supplied to the algorithm will be almost similar to the format in which output is expected, and we need to compute the running time of an algorithm. So, this analysis will be referred as best case analysis. We can say if we sort the n numbers in ascending order and the element and our input is already given in ascending order, in that case we can find this is the best case algorithm. And whenever we execute that given n numbers which is already sorted in ascending order, so in this case we can get in minimum time, because already input is already sorted. Next is worst case. How we analyze the worst case? So, we need to look at the input data and determine an upper bound. We can say big O notations in terms of asymptotic notation. So, on how long it will take to run the program. Analyzing the efficiency of an algorithm in the worst case scenario speaks about how fast the maximum runtime, that is the worst case, or we can say layman approach. In layman approach, that will be the maximum time it will take. So, when we increase the input size, it will take the maximum time. So, for example, if we would like to sort a list of n numbers in ascending order, a list is given in descending order, because this is the worst case scenario. If the list is already given in descending order and we have to sort it in ascending order. So, in this case we will find that scenario is satisfied to the worst case. Okay. Next is average case. So, in average case we need to look at the time required to run the algorithm where all inputs are equally likely. Like when we talk about the theta notation, in case of theta notation, all the inputs have possibility equally likely. So, analyzing the efficiency of an algorithm speaks about probabilistic analysis by which we find expected running time of an algorithm. Okay. So, for example, in a list of n number be sorted in ascending order, and some numbers may be at their required position and some are not at the required position. That means we can say the elements are input in jumbled order. Jumbled, maybe it may increasing, decreasing, or there is not a specified way of entering the number. So, in this case when we sort that element, this is the case of average case. Next is how these efficiency are analyzed. So, during efficiency analysis of algorithm, we are required to study the behavior of algorithm with varying input size. Okay. So, for doing the same, it is not always required to execute on machine, or number of steps can be computed by simulating or performing dry run on an algorithm. So, generally in case of analysis of efficiency, we think about the how many number of steps are there and how many executing steps are there, and so that is the scenario of efficiency in efficiency analysis. So, for example, consider the linear search algorithm in which we are required to search an element from a given list of element. Let us say size of the list is n. So, how we analyze that to how to analyze the number that number is present in the given list or not. So, it all comes under the efficiency analysis. So, if we see here the linear time algorithm, we are talking about the linear time complexity. So, we have a input element, an array of n numbers, and an element which is required to be searched in the given list, and what will be the output? Output we have to tell that the number exists in the list or not. Okay. So, input is an array of n numbers and an element which is required to be searched. So, what is the algorithm? First input the size of list, that is the size of list, that is n. Read the n elements of an array, input the item or element to be searched in a given list. So, first we have to focus what are the input. Input is array of n number and the element which is required to be searched. Okay. So, so for each element in the array, here we use, because we have to search a particular element like x. Suppose we have to search x in the given list, that is 1 to n, that is given in array. So, that element x is present or not. So, for this we have to use the looping instruction. For I equal to 1 to n, we can use for loop or while loop, whatever the loop is required. So, for I equal to 1 to n, if ai means the element which are present on the ith position in array, and that equals to item. Item means that element to be searched, which element. If this ai equal to item, that means that element is present, that is search successful, and this ai equal to item will be within the for loop, while loop, whatever the looping instructions will be there. So, if we meet ai equal to item, that search is successful, and return if I equal to n plus 1, that means we iterate 1 to n and the element is not matching with ai, that means I equal to we reach I equal to n plus 1, and in that case element is not present, that is we can say search is unsuccessful, and we have to stop here. So, efficiency analysis of the above algorithm, that is the searching algorithm, that is linear search, how to analyze these efficiencies. So, in at what case we can think the worst case. So, in respect of example under consideration, the worst case is when the element to be searched is either not in the list or found at the end of the list. It may be possible the element is reside on like nth position in an array, or it may be possible it will not present in entire list. Okay. So, we have to traverse from array 0th index to, or we can say first index to last index. Element, it may be possible it will be present at the last index, or element is not present in the list. This is the worst case scenario. So, in this case algorithm runs for longest possible time, that is maximum running time of an algorithm depend on the size of an array. So, if we consider the element having n element, so our search will happen from I equal to 1 to n, that is this is the case we can say the worst case time complexity of linear search is big O of n. Big O of n means this is the worst case time. Okay. Next efficiency is average case. So, what is the average case, in what scenario linear search perform the average case. So, in this case expected running time will be computed based on the assumption that probability of occurrence of all possible inputs is equally. So, we can say the case of equally likely, maybe it will that search element is present at position 1 or 2 or 3 or n, all position have been equal chance. So, array element could be in any order. So, this provide average amount of time required to solve a problem of size n. Respect of example under consideration, element could be found at random position in the list. It may be possible it is found on index 0 or index 1 or index 2, or it may be possible it will found in order nth position. So, we can say the time complexity will be big O of n, and at what condition is it is considered as the best case. So, in this the running time will be fastest for given array element of size n. It gives minimum running time for an algorithm. In respect of example under consideration, the element to be searched is found at first position in the list. Okay. So, if we have the n element in the list and the element which we want to find in the list will be present at the first position. That means, whatever the size of the element, it will we can find it in constant time, that is order of 1 time. So, running time complexity in this case for linear search is big O of 1. Okay. So, overall we have analyzed the best case, worst case and average case. So, in most of the cases, average case analysis, worst case analysis play an important role in comparison to best case. Okay. So, worst case analysis define an upper bound, that is we can say big O, upper bound on running time for any input size. Okay. And the average case analysis define expected running time, because all element have equal probability or equally likely situation to present in the list for input of given size, that is equally likely. For solving a problem, we have more than one solution. Okay. Comparison among different solution provides which solution is much better than the other, that is which one is more efficient. What we talk about the more efficient, that means more efficient means in terms of time complexity, which will take lesser time. If we compare big O of n square, big O of n log n, n log n. So, because in all the scenario, if we say we have to solve that problem in big O of n time or big O of n log n time or big O of n square time. So, in terms of efficiency, which algorithm will be taken into consideration, which have a lesser time. Okay. If we compare of order of n square or n log n or order of n obviously will be preferable. Okay. So, efficiency of algorithm depend on time taken to run the algorithm and use of memory space by the algorithm. One more consideration is also there, that is the space complexity, but generally in this course we will talk about the time complexity. In terms of time efficiency, which algorithm will be best, that will be taken into the consideration. So, execution time of an algorithm will be computed on different sizes of n. For large value of n, constant factor will not affect the complexity of an algorithm. Hence, it can be expressed as a function of size n. Okay. So, for example, big O of n equal to big O of n by 2 or big O of n plus 2, etc. It is read as order will be defined in terms of n irrespective of the constant factor like divide by 2, plus 2, minus 2, etc. As while discussing complexity analysis, we are interested in order of algorithm complexity, because when we talk about the constant factor, if I say the time complexity is order of n or order of 2n or order of n by 2 or n plus 2 or n minus 2, generally constant factor we can ignore the constant factor and straightforward we can say the time complexity will be big O of n. So, generally we consider the complexity in terms of big O of n or n by 2 or n plus 2 or n minus 2 or 2n. In this way, we consider the time complexity and remove the constant factor. So, we do not think about the constant factor. Okay. Comparison, when we compare the different efficiency of an algorithm, we have a table. I tabulated the something all the time complexity and the explanation respectively. So, running time for most of the algorithm falls under the different efficiency classes. That is, if we say symbol, we can say big O of 1, that is the constant time, in which scenario we can get the constant time algorithm. When instruction of program are executed once or at most only a few times, that is we can say 1 time, 2 time or 3 time, that is the constant time, then the running time complexity of such program is known as constant time. Like we can say, if we have written instruction x equal to y plus z or something x equal to y minus z, okay, or we initialize I equal to 2. So, this type of instruction will take constant time. So, it is independent of the problem size. So, it is referred as big O of 1. For example, we can say linear search best case complexity, when we compare the first element with the target value and it will match. So, this comparison comparison things will take constant time, that is the big O of 1. Next algorithm is logarithmic complexity. Okay, we can say big O of log n. Okay, so the running time of the algorithm in which large problem is solved by. So when we talk about the logarithmic complexity, the running time of the algorithm in which the large problem is solved by transforming into a smaller size sub problem is said to be logarithmic in nature. Like we can say a divide and conquer rule. When we have a problem of size n, and each iteration we divide that size by n by 2 or n by 4, n by 8, something like that. So at each iteration problem size will be reduced. So in this case the logarithmic time complexity will the time complexity value will be logarithmic. So in this algorithm becomes slightly slower as n grow. It does not process all the data elements of input size n. The running time does not double until n increases to n square. So it is represented at big O of log n. For example, binary search algorithm running time complexity is big O of log n. Generally what we do in binary search algorithm, at each iteration we compare the mid element. If the search element is less than the mid element, we go to the first half, or that is left half. If the search element is greater than the mid element, we go the right half. So at each iteration we left the one half. So if the initial problem size is n, the next side problem size is n by 2 and the next is n by 4. Similarly, when the problem size become 1, that is the sub problem size become having the size 1, the algorithm stop. So in this way, because the n if we say after kth iteration n by 2 or n by 2 to the power k equal to 1, that is 2 to the power k equal to n, that is k equal to log n. So in this case we can say the complexity will be logarithmic. Next is linear time. So at what condition we can get the linear time complexity? So in this case the complete set of instruction is executed once for each input, that is input of size n is processed. So it is represented as big O of n. This is best option to be used when the whole input has to be processed. So in this situation time requirement increases directly with the size of the problem. So for example, linear search worst case complexity is big O of n. Like I already discussed, when it will come big O of n in the case of linear search, if the element is either it will be present at the nth position or when the element is not present in the list. So in this case in case of linear search we can get the worst case time complexity. Next is quadratic. When we get the quadratic time complexity, so running time of an algorithm is quadratic in nature. When it processes all pairs of data items, such algorithm will have two nested loops. Generally we talk about the nested loops, and one loop, one outer loop and one inner loop. In this case, if the outer loops execution is like n size and the inner loop execution is also having n size, in that case if we execute any statement within the inner loop, we can get the quadratic or n square time complexity for input size n. Okay. So practically this is useful for problem with a small input size or elementary sorting problems. Okay. Like when we sort the 10 elements or 20 elements, when we want to sort maybe millions of data or trillions of data, in that case big O of n square is a very big number or very big, it will take lots of time. So in this situation time requirement increases fast, because this growth n square growth is very fast with compared to the big O of n. So in this situation time requirement increases fast with the size of the problems. Okay. So for example, insertion sort running time complexity is big O of n square in worst case. Okay. We can say in worst case it will take big O of n square. Next is exponential time. Okay. So this time complexity will happen, or we can this exponential time complexity achieved like an example of tower of Hanoi problem. So, running time of an algorithm is exponential in nature if brute force solution is applied to solve a problem. Okay. So, in such problems, in such algorithm, all subset of n elements set is generated. In this situation, time requirement increases very fast with the size of the problem. So, for input size n, running complexity expression will be 2 to the power n. So, for example, Boolean variable equivalence of n variable running time complexity is big O of 2 to the power n. Okay, that is the exponential time complexity. In case of tower of Hanoi problem also, we can get the big O of 2 to the power n. So, next how that complexity will increases as the value of n is increases. When the value of n equal to 1, constant time will take 1 and the logarithmic time will be also 1. When we increase the value of n and we can see the different complexity have the outcomes. Okay. So, when the value of n equal to 10 to the power 2, the exponential value is 10 to the power 3, 10 to the power 30, and in case of quadratic it will value 10 to the power 4. When the value of n equal to 10 to the power 4, the linear time is 10 to the power 4, a quadratic time 10 to the power 8, and the exponential time it will 10 to the power 3010. So, we can say how this complexity, how this constant logarithmic linear quadratic exponential will grow after the size of n is increases. Okay. So, if we can discuss the insertion sort algorithm for j equal to 2 to like we want to sort an element having n element, and what will be the algorithm for j equal to 2 to a dot length. A means the array having n element. Okay. So, first we want to keep key value, that is a j, and I equal to j minus 1, and while loop we can consider I greater than 0, I greater than key, and if we assign a I value to the a I plus 1, and correspondingly we can decrease the I value, and finally assign key value to the a I plus 1. This insertion sort, if we compare the logic of this insertion sort, input is given n input elements, output is number of steps incurred to sort a list. So, what is the logic behind it? If we are given n elements, then in first pass it will make n minus 1 comparison. Okay. In second pass it is the maximum n minus 1 comparison, in second pass maximum n minus 2 comparison, third pass n minus 3 comparison. So, total number of comparison if we count, that is n minus 1 plus n minus 2 plus n minus 3. So, if we add them, we can get the order of n square. So, therefore, the insertion sort algorithm encompasses a time complexity of big O of n square and a space complexity big O of 1, because it necessity that some extra memory space for a key variable to perform swap operation. Okay. So, if we compare the time complexity in insertion sort, for best case complexity, the insertion sort algorithm has a best case time complexity of big O of n for already sorted array, because here only the outer loop is running n times and the inner loop is kept silent. Here we can see if the element is already sorted, the outer loop, that is for j equal to 2 to a dot length, it will move or it will incremented, but when we go to the inner loop, that condition must be satisfied I greater than 0 and a I greater than key. If the element is sorted, then a I greater than key, this condition will be false. So, the inner loop does not execute. So, in best case only outer loop will execute. So, the time complexity of the time complexity is big O of n. When we want to execute the average case time complexity, so the average case time complexity for the insertion sort, that is of big O of n square, which is incurred when the existing elements are in jumbled order, okay, neither in ascending nor in descending order. In case of worst case time complexity, the worst case time complexity is, and in average case also it will be the big O of n square, and in worst case also it will give the order of n square time complexity, which occurs when we sort the ascending order of an element of an array into the descending order. In this algorithm, every individual element is compared with the rest of the element due to which n minus 1 comparison are made for every nth element. So, the insertion sort algorithm is highly recommended, especially when a few elements are left for sorting, or in the case the array encompasses few element. Okay. So, and what will be the space complexity? Space complexity for insertion sort is big O of 1 due to usage of an extra variable key. Next is binary search. If we compare the binary search, because we already compare the linear search, and the next is like insertion sort for big O of n square, like quadratic, and for logarithmic complexity we can take the example of binary search. So, in this case the binary search iterative method, here we comparison what will be the parameters of binary search, that is the array element x is the element you want to search, and low and high means low and high is the index point, okay, for an array. So, when we see the binary search algorithm in at while loop, in while loop low is less than equal to high, and we calculate the mid position, and the mid and array of mid position and the value you want to search, that is the data point, a key point you want to search. If match, that return mid, or if x is greater than mid, then low equal to mid plus 1, or else high equal to mid minus 1. Either it will go the first half or next half, or left half or right half. Okay. So, the same way we can see the recursive method also. Here we also calculate the mid position, mid and the array of mid and the value you want to search. If it is matched, then return mid, or it will go in first half or second half, okay, left half or right half. So, what will be the time complexity in this case? So, in the best case, the time complexity of binary search for a list of size n is big O of 1, because it is the independent of the input size n. In other words, the time complexity of binary search depends upon the best case, as the key is matched with the mid element. Okay. And at what case the average case, its time complexity will be big O of log n. The average case arises when the target element is present in the some location other than mid index. Okay. So, the time complexity depends on the number of comparison to reach the desired element. Okay. Therefore, the overall average case time complexity of binary search is big O of log n. Okay. And at what case the worst case scenario will arrive? So, the worst case scenario of binary search occurs when the target element is smallest element or largest element, okay, of the sorted array, because in when we apply to the binary search, the element will already sorted. So, since the target element is present in the extremity means either it will be at first index or last index. There are log n comparison in total. So, therefore, worst case time complexity of binary search is big O of log n. So, in recursive implementation also, overall space complexity will be log n, and in iterative case it will be big O of 1 for space complexity. So, when we how that value log n came, we can see at iteration 1 length of array equal to n, at iteration 2 that it will consider our left half or right half, the array size become n by 2, again the array size will become n by 2 to the power 2, and after kth iteration the array size length of the array is n equal to 2 to the power k. When we know that after kth iteration the length of the array becomes 1. So, n by 2 to the power k equal to 1. So, n equal to 2 to the power k. So, k equal to log n, that is the average case or worst case time complexity. So, these are these all are the complexity of linear search, quadratic search or logarithmic search. So, and in case of tower of Inouye or brute force approach, we can say the exponential time complexity also. So, thank you.